So now that we've introduced ourselves to growth or decay model, what it really, we have growth again being a to the x and decay being a to the negative x, where our a is greater than 1. All right, so that's basically what we saw out of those two models, growth or decay. And it turns out that there's two very famous exponential models. The first one is when the base is 10. So we're either talking about 10 to the x or 10 to the negative x. Again, as we saw, the basic behavior is essentially the same. 10 to the x will still be going through 0, 1, right? And it's going to go up, and it's going to go here, and it's going to go up pretty fastly, right? Just at 1, we're already, 10 to the first power is 10. So it's going to go up pretty quick, all right? And then 10 to the negative x, well, again, like any classic decay model, it's still going to go through 0, 1, but it's going to come down fast and then slowly start doing that number, right? Reason why 10 to the x is so famous, right, is because of what we're going to find to be its inverse later, right? I think in 6.4, 6.5-ish, we're going to learn that the inverse of this function is log base x. Now, why that's the case, I'll explain when we get there, but that's why 10 to the x is so famous, because we do a lot of things in science and engineering that involves logarithms, or log base 10, so logarithm. So because the log base x is so famous in applications in science and whatnot, its inverse function, 10 to the x, also is relatively famous. I think another reason why this particular exponential function, base 10, is so famous is because we live in a base 10 world, right, in terms of our decimal system. So that's another reason why that comes up quite frequently. Now, another one is base e. So e to the x and e to the negative x. So the first thing I need to do is convince you that this e is actually a number. And there's a lot of ways to actually compute it, but it turns out that e, right, is a number. It's actually a limiting value to that crazy function, right, as n goes to infinity. So let's go ahead, since we have technology, let's do an investigation, right? And what I've already started with my Desmos is I've already started with n equals to 1. So when n equals to 1, we get an approximate value of e being 2, right? But our n value here is going to infinity. So let's see if I change it. Let's let n equal 10. Let's just start getting big quick. So I got to change that to a 10. And I got to change that to a 10. And what we get is this is estimating e to be 2.59374. So it's starting to grow. All right. Let's go to n equals 100. Right. So I'll change that to a 0. Let me get up there. I'll change that to a 0, and we end up getting that e is approximately 2.7048 yada yada. Right? What happens if I change that to 1,000? Right? So throw a 0 there, put another 0 there, and we get e is roughly 2.7169. So you can already start to see we're continuing to increase, but between n equals 100 and n equals 1,000, right? The value, our approximated value of e, didn't change much, right? It's 2.7, 2.7. The only thing that changed was that next decimal. So let's go one more. Let's go out to 10,000. Right? So let me tack on another 0. Let me tack on another 0. And what we get is e is roughly 2.718149. And so you can see by going up 10,000, right? That's a lot. The first decimal didn't change, the second, the third one, and then the third one came up a little bit. So it turns out that e itself, right, I'm going to stop that. There's a little bit of investigation. It actually came up through the study of logarithms, believe it or not, and also with recurring money. For those of you who know the compounded interest formula, you can kind of see that in that formula right there. But at any rate, what we have established is that e is approximately 2.71. which makes it a number that's greater than 1. So that means what's the e to the x graph going to look like? It's going to look like a classic exponential growth curve. What is e to the negative x going to look like? It's going to look like a classic exponential decay curve, because that e, that crazy letter, right, actually represents a number for those of us in mathematics. Where did this come up? Right? Well, again, it's going to come up because as we mathematically model things and we solve the equations, it turns out that the variable e, this guy right there, keeps popping up over and over and over again. The math's going to look quite complicated, but when we talk about the change in population over the change in time, right, the population is proportional to whatever the population is at any time, right? So the higher my population is, the more my rate of growth is going to be. If my population's small, the rate of growth is going to be small. And when you guys go to calculus and you solve this, what you're going to end up finding is that P of t is some constant e to the negative kt. And again, I'll actually explain we'll see what the a and the k are later in this class. We actually don't need calculus to analyze it, but you can see by taking this mathematical model that does population growth, as we solve it using mathematical ideas, the letter E came up, right? It's not the letter E, it's the number E. And so it comes up very naturally in a lot of recurring phenomena, whether it's population dynamics, whether it's the spread of a virus, whether it's money that's growing or decaying, radioactive decay. When we mathematically model them using our math models and using our calculus to solve, we end up with E. And so that's why this particular exponential function is so famous, because it's actually very applicable and related to some inverses that we're going to find. You guys have probably seen this before. The inverse of this guy is famously known as the natural log of x. And the reason why we call that the natural log of x is because E occurs so naturally, right, in our real world, and so its inverse, right, the way we reverse that, we give it the name the natural log of x. But more on that as we go into 6.4 and 6.5. What I wanted to do is, after talking about growth and decay models, I wanted to just revisit, because we talked about base 2, base 3, base 4, I think 5, but it turns out that when you guys get into the real world and start applying them, you will see a lot of base 10s because you'll see logarithms, right? And you'll see a lot of base e's because you'll see a lot of natural logarithms, all right? And so just want to get you guys prepared for seeing that and doing a little analysis. As far as we're concerned, their basic graphs remain the same, right? 10 to the x and e to the x behave just like exponential growth models should. 10 to the negative x and e to the negative x behave just like exponential models should. So their graphs are the same, their behaviors are the same, their characteristics are the same. It's just that they're very famous because they do come up in some very famous applications. Right? So I just wanted to address that, give these two famous functions their limelight. Talk to you guys later.